Hello friends, welcome to P.Campoint. Today's topic is crystal field theory. This theory is proposed by Bethe and Van Vleck. Main point of this theory is that this theory considers metal ligand bonding to be purely electrostatic in nature. Electrostatic means in which we have positive and negative charge species and in which we discuss about these interactions. Same type of interactions are found in ionic crystal. That is why it is named as crystal field theory. Now, according to this theory, ionic ligands such as Cl negative, OH negative, Cn negative, these are considered as negative point charges. And neutral ligands such as H2O, NH3, they are considered as dipole, in which we have two poles. Like in this NH3 ligand, this is negative pole and this is positive pole. This negative pole is always directed toward metal cation, which is positively charged. Metal cation is positively charged. Similarly, in this H2O ligand, this is negative pole and this is positive pole. This negative end is always directed toward this positive metal cation. These are the basic postulates of crystal field theory. After this theory discusses about crystal field splitting in octahedral, tetrahedral and square planar complexes. To understand them, firstly we should know about shapes of d orbitals. As we know that there are basically 5 main d orbitals. 3 of them is dxy, dzx and dyz. These orbitals lies in between the axes, as this is dxy orbital and lobes of these orbitals lies in between x and y axis. Similarly, dyz orbital in which lobes lies between y and z axis. Another one is dzx in which lobes lie between x and z axis. Another two orbitals are dx square minus y square and dz square, and these two orbitals lies on the axis. Like this is dx square minus y square orbital, and in which lobes lies on x and y axis. This is dz square in which lobes lie on the z axis. These are the shape of all the orbitals, and now we will move toward crystal field splitting in octahedral complexes. And now crystal field splitting in octahedral complexes. As we know that octahedral complexes have 6 number of ligands. So this is an octahedral complex. M is representing metal cation, L is ligand and there is 6 number of ligand. This is the charge on coordination complex. So in this we will consider that metal ion is placed in the center of octahedron and all the 6 ligands are placed on the 6th corner of this octahedron. Also, these corners are directed along Cartesian coordinate x-axis, y-axis and z-axis. Okay. First situation is that when all the 6 ligands are at infinite distance from the metal cation, this is metal cation and ligand is at infinite distance. The distance between this metal cation is L is infinite. Then the 5d orbital of metal cation will not be affected by ligand electrostatic field and will remain degenerate. Degenerate means that the energy of all d orbitals remains same. This is representing the situation in which energy of all d orbitals is same in case of free ion or ligands are at infinite distance. Now, when these ligands move toward the metal cation, when the ligand is approaching toward metal cation, there are two electrostatic forces. One is attraction between metal cation and ligand. Metal cation is positively charged and ligand is negative charged. So there will be attraction between them. Second is repulsion between d electrons of metal cation and lone pair of electron on ligand. This is repulsion. So, due to this repulsion, potential energy of the metal d electron increases. This is showing the increase of energy of the metal d electron. Now, if all the 6 ligands approaching to the metal cation surrounded it is spherically symmetric, then the d orbital will remain degenerate. That means that if there is spherical symmetric field, then this energy remains the same. But this is in hypothetical situation. What actually happen is splitting, which is due to the different shape of d orbitals. These are the 3 orbitals which lies in between the axes, and these orbitals lies along the axis. And this is also the direction of approaching ligand. So there will be greater repulsion between them, and their energy is increased to the higher level in this manner. And these 2 orbital is named as Eg orbital. And now these orbital, which is lying in between the axis, is far away from the direction of approaching ligand, so there will be very less repulsion between them, and their energy is decreased to a lower level, and they are named as T2G orbital. Okay, distance between this T2G and EZ orbital is known as crystal field splitting. Crystal field splitting, represented by delta O. Also, the total increase in energy is always equal to total decrease in energy. The decrease in energy is stabilized by minus 0.4 del naught or 4 dq, and total increase in energy is stabilized by plus 0.6 delta O naught or plus 6 dq. This is all about crystal field splitting in octahedral complexes. First case is when there is no splitting, and then there will be increase in potential energy of d orbital. And after that, when the ligand come very close to the metal cation, there will be splitting on the basis of different shapes. That will give us T2G and EZ orbital, and the difference between them is CFSC, which is crystal field stabilization energy delta naught, increases plus 0.6 and decreases minus 0.4. This is all about crystal field splitting in octahedral complexes.